So now we're going to take a look at what we do when we have a small sample and we have an unknown population standard deviation. So again, if we refer back to our table here, we can see that small sample, unknown population standard deviation means that we are going to use T. So that means for these questions, where we have a small sample unknown population standard deviation and we have two sets of data, we are going to be doing a two sample t-test. So when we try to compare the mean of two populations, when we have a small sample and an unknown population standard deviation, we have to do the calculation in two steps. So our first step is to find the estimate of the variance, which is officially called the pooled estimate for the variance, which uses this formula here. SP squared equals nx minus 1 times the variance of the first group standard deviation of the first group squared, plus the number of pieces of data in the second group minus 1 times that standard deviation squared, divided by the number of sets of data in the first group, plus the number of sets of data in the second group, minus 2. And the reason why we're minusing 2 this time is because we have two sets of data. Now you don't need to worry. You don't need to remember this formula. This formula is given to you on page 6. So this is in our formula booklet on page 6. And notice how it is the sample standard deviation, because as we said here, it's an unknown population standard deviation that we have. Also on page 6, we have our formula. And again, similar to when we were looking at the two sample normal test, the formula in the formula booklet is slightly different. So the one in the formula booklet looks like x bar minus y bar minus mu x minus mu y divided by the square root of SP squared 1 over nx plus 1 over ny. So you can see the similarity here. We are going to be using, without this part here, just like we do with the other one. You can either think of it as you're missing the beginning or missing the end, but you're only using one of these brackets. This time, we are going to be using get our critical value from our tables. So to get that from our formula booklet, we're looking at page 19. So this is on page 19. And this is the same table as we used when we had our single sample t-test. And that means that if you remember, if it's a one-tailed test, we just do 100% take off that significance level and look down from that percentage. If it's a two-tailed test, we half the significance level and look down for that percentage. And down the side, we have the little v, which stands for degrees of freedom. And as you can see here, the degrees of freedom for this test, we're going to be adding the number of sets of data that we have in the first group together with the number of sets of data we have in the second group, and then we are going to take off 2. So as with the normal distribution with the two sample means, if we are using different symbols, we have to define what those symbols stand for. And that's very important so that anybody who reads our hypothesis test knows what we are looking at. So we're going to have a look at the first example. Like I said, these are quite tricky, but after you've done a couple of examples, they get a lot simpler. So we've got Mr. Brown is the owner of a bakery in a large town. He believes the smell of fresh baking will encourage his customers to purchase bread from the bakery. To investigate this belief, he records the daily sales for 10 days when all the bakery's windows are open and 10 days when all of them are shut. So it's very important to notice that this is two samples of data. This is not paired data. Even though we have the same amount of opening and being shut, it's not paired together with anything. It's not that this value here was on Mondays, this one here was on Tuesdays, and so on. It's just here is 10 random days where it was open, here is 10 random days when it was shut. So just be careful with that, because we are going to come on to what you have to do if it is paired data later on. So then we're trying to investigate his belief at a 5% significance level. So he believes that the smell of fresh baking will encourage customers to purchase baked bread from his bakery. So our H0 is going to be that the mean when it was open is equal to the mean when it was shut. And he believes that because the smell is going to encourage customers, that means that the mean when it is open should be more than the mean when it was shut. And we have to define these symbols. So our mu O is going to be the population mean daily sales with the windows open, and then we're going to have mu S, which is going to be the population mean daily sales with the windows shut. Okay, so now we need to find out the information about this data, just as we did with the two sample normal. I know that this is normal, this is T, sorry, instead of normal, because nowhere here has it given me the standard deviation. Okay, so I'm going to have to find it for these sets of data. So we're going to have a look at O and S. So in my calculator, in the stats part, I'm going to delete anything I already have in there. And then I'm going to enter my data for when the window was open. So that's 202, 204.5, 207, 215.5, 190.8, 215.6, 208.8, 187.8, 204.1, and 185.7. And as always, double check that you have entered all the pieces of data incorrectly, because we are going to get our values straight from the calculator, which means that if I've typed one of these values in incorrectly, I'm going to lose marks. Then we go into calc, check that your set says list 1, 1, because we put our values into list 1 and we don't have any frequencies. And then we want to go to 1 var, and we're going to need to write down the sample mean, the sample standard deviation, and the number of pieces of data in the sample for each one. So for the first one, we've got 202.18. For the sample standard deviation, we've got 10.7577155. Notice how I have kept lots of significant figures here, because I'm going to be doing future calculations with it, so I want to keep as much accuracy as possible. And my N is 10. Just change my symbols there so that it matched up with my subscript here. So for S, we're going to have the mean of shut. Sorry, that's very funky. We're going to have the sample standard deviation of shut, and we're going to have the number of pieces of data of shut. So again, delete what we have in there. And then we're going to type in our shut piece of data. So 193.5, 192.2, 199.4, 177.6, 205.4, 200.6, 181.8, 169.2, 172.2, and 192.8. And again, quickly double check that you've entered those incorrectly into your calculator. And then we want to go to calc. Your set should be the same still. And then we go to 1 var. So this time our mean for the shut is going to be 188.47. The sample standard deviation is going to be 12.5161273. And then the number of pieces of data that we have is 10. So now we need to use our formulas. So because, if I just scroll up a bit, because this formula here contains SP squared, which we find using this formula here, we're going to use this one first. So that's going to give us SP squared is equal to 10 minus 1 times 10.7577155 squared plus 10 minus 1 times 12.5161273 squared divided by 10 plus 10 minus 2. So we're going to put that in our calculator. So go back to the normal maths part. So we've got 10 minus 1 times 10.7577155 squared. Oops, sorry, one too many sevens has gone in there. And one too many fives, there we go. Plus 10 minus 1 times 12.5161273 squared divided by 10 plus 10 minus 2. And that gives us an SP squared of 136.1909427. And again, because I'm going to be using this in a future calculation, I have written the whole thing down. So to get our test statistic, our t value, we're going to have to use the other formula. So we're going to have 202.18 minus 188.47 divided by the square root of SP squared, so 136.1909427 times 1 over the first n plus 1 over the second n. So again, in the normal part of our calculator, fraction 202.18 minus 188.47 divided by the square root of our SP squared, which is the last thing that I put in my calculator, so I'm just going to use my answer key, times 1 over 10 plus 1 over 10 and that gives me a test statistic of 2.63 to 3 significant figures. So we're asked to use a 5% significance level. Our degrees of freedom, if you think about what I said before, our degrees of freedom is going to be 10 plus 10 minus 2, which gives us 18. So we're looking down from 0.95 to n is 18. And that gives us a critical value of 1.734. So in the same way as we had For the one sample t-test, if our test statistic is bigger than our critical value, we're going to reject. If our test statistic is less than our critical value, we're going to accept. So here we are going to reject. So as the test statistic is bigger than the critical value, we reject H0 at a 5% significance level. There is sufficient evidence to suggest the mean sales on days when the window is open is more than when the windows are shut. Now, as we had when we were looking at the two sample T, there are some assumptions that go along with this. The data has to be normally distributed the population has to be normally distributed and the sample has to be a random sample. So just checking here, it does not mention that the daily sales are normally distributed, and it does not state that the days when the window is open and closed are a random sample. So I'm going to add those on as assumptions. So our assumptions here the daily sales, and this is for when the window is opened or shut, are normally distributed because it's a small sample, and it'll always be a small sample with the t-test. And the sample of days is a random sample, and that is always having to be true. So, having a quick look at our second example here. So this time we've got the website reveals that 2 random samples were taken. In June, before the new one-way system came in, a sample of 8 drivers were timed from leaving Carpenter Estate to arriving at the town hall. A second sample of 9 different drivers were timed over the same journey in August, the day after the new system was introduced. These are unpaired samples since the Avonford Star did not choose the same drivers. This could be because the drivers did not do the same journey in June and August. The data were as follows. So we can see here that we've got a small sample, we've got the mean, and we only have the standard deviation that's out of that sample. So because it's a small sample and we only have the standard deviation of that sample, that means that we are going to use T because it falls into that box. So always think back to your table. Do I have a small sample? Do I have the sample standard deviation? In this case, yes, so it's going to be T. So, do these confirm Avonstar's conclusion that the traffic system has got worse by extending the time by more than 4 minutes? So, because it says here by more than 4 minutes, not just by 4 minutes, it says by more than 4 minutes, that means that this is a one-tailed test. And remember, just the same as we did when we were talking about the 2-sample normal, we have to be careful for that language there. So our H0 is going to be that mu j, which one's meant to be the shorter one. Just double checking. The website, so they think that it's going to be by more than 4 minutes. So they're saying that June's going to be the quicker one. So they're saying that even if they added 4 minutes onto June, that's still going to be shorter than in August. So H1 mu J plus 4 is still shorter than mu A. Now, I don't like my hypothesis being these ways round. You can do it this way round. That'd be fine. It'll give you the same answer, but usually I do it the other way around so that the smaller one is on the right hand side. Just as we had before, we're going to have to define these symbols. So mu J is the population mean travel time in June, and mu A is the population mean travel time in August. Now this time, very nicely, we don't have to figure any of the values out. They've already been given to us here, so we can dive straight into finding SP squared. So our SP squared is going to be 8 minus 1 times 1.08 squared plus 9 minus 1 times 1.88 squared divided by 8 plus 9 minus 2, which gives us 8 minus 1 squared, times 1.808 squared. Always be careful, that's a common thing that the squared sign goes in the wrong place. Times 1.88 squared divided by 8 plus 9 divided by 8 plus 9 minus 2, and that gives us an SP squared of 2.429333333. And again, you can see that I haven't rounded it there because I'm going to do a further calculation with it. So then to find our test statistic, this time, remember that we're wanting to move it all onto one side. As I've said before, I like to keep it so that it's going to be positive, so I'm going to take it to the right hand side in this case. You could take it to the left hand side and you'd end up with the same value. It would just be a different sign, and then you'd have to use your modulus line. So I'm going to show it that way actually, and then I can show you what we do when we've got a negative. So we're going to have, moving the mu A to the other side, we'd have mu J, which is 23.78 plus 4 minus 28.4, still divided by the square root of our SP squared, so 2.429333333, 1 over N1 plus 1 over N2. So the reason why this is as it is that we've used T equals, we've moved this to the other side. So if you remember, I talked about this in the 2 sample normal video. We're rearranging that in the same way. So I'm leaving my mu J plus 4 on that side, and I'm moving my mu A to the other side, and that's what then goes on the top. The bottom stays the same, so that stays as SP squared 1 over NJ minus 1 over NA. Sorry, plus 1 over NA. So then we can put this into our calculator. So we've got fraction 23.78 plus 4 minus 28.4 divided by the square root of our SP squared, which is our answer, times 1 over N1, which is 8, plus 1 over N2, which is 9, which gives us minus, so at this stage our test statistic is minus 0.8186342721. You don't have to write the whole thing down. In order to do my comparison, I want to see the size of this. So the size of my test statistic is just going to be 0.819 to 3 significant figures. Looking at the critical value, again, it's one-tailed, so we're just going to stick with, doesn't give us a significance level. So remember, if it doesn't tell you, use 5%. So we're looking down from 0.95. Our degrees of freedom is going to be 8 plus 9 minus 2. Remember, add the number of pieces of data you've got in each group together and take off 2, which gives us 15. So going down from 0.95 to 15, which gives us a critical value of 1.753. So that means as this time the size of our test statistic is smaller than the critical value, we end up accepting H0 at a 5% significance level. There is insufficient evidence to suggest the mean travel time in August is more than 4 minutes longer than in June. And again, just double checking up here, it doesn't say that these were normally distributed. It just says a second sample, a sample of 8 drivers, so it doesn't state that these are a random sample, so we're going to have to write those down as assumptions as well. So our assumptions here is that the journeys in June and August are a random sample of journeys or journey times, and that the journey length in June and August are both normally distributed. So if you had rearranged it the other way, like I said, the way that I usually like to do it, then the main difference would be that these would be the other way around in your numerator. If that happened, just to show you what that would give you, that would give us 28.4 minus 23.78 plus 4, making sure you've still got it in a bracket, which gives us 0.819 to 3 significant figures there. So like I said, it just makes the sign the opposite. So that's why I like to make it so that I'm ending up with something that's bigger than 0. So as I said, the assumptions are that the population is normally distributed and that the sample is a random sample. So make sure, if it doesn't state this in the question, that you are writing it down as assumptions to make sure that the test was definitely valid to use. So I'd like you to pause the video now and give these 2 Now You Try questions a go. Okay, so hopefully you've given the first Now You Try question a go. Sorry that I've run out of space a little bit writing on here. So we have a random sample of 10 hot drinks from dispenser A had a mean of 203 millilitres and a standard deviation of 3 millilitres. A random sample of 13 hot drinks from dispenser B had a mean of 206 millilitres and a standard deviation of 5 millilitres. Test at a 5% significance level the hypothesis that the drinks from dispenser A are on average 3 millilitres more than from dispenser B. So because it says more, it says 3 millilitres more, not more than 3 millilitres more or less than 3 millilitres more. It just says 3 millilitres more. So it's either is 3 millilitres more or it's not 3 millilitres more. So this is a two-tailed test. So our H naught is that mu A equals mu B plus 3 because the B is going to be the smaller one. So that's why we've added the 3 onto that one. And our H1 is going to be that mu A is not equal to mu B plus 3. And again, you can see that I've defined what mu A and mu B mean. So we've got the population mean amount of drink dispensed from A and the population mean amount of drink dispensed from B. I've then summarised what was written in the text part here. Use my SP squared formula, which was 10 minus 1 times 3 squared plus 13 minus 1 times 5 squared, all divided by 10 plus 13 minus 2, which gave me 127 over 7. So it gave me an exact fraction, so I just kept it as that for my working. Then I had to use my T formula. So if I was taking my mu B plus 3 to the other side, I'd have mu A, which is 203, minus mu B plus 3, which is 206 plus 3, divided by the square root of SP squared, which is our 127 divided by 7, times 1 over N1, which is 1 over 10, plus 1 over NB, which is 1 over 13. And that gave me a test statistic of minus 3.348. So then, because I want to make that positive, the size of my test statistic is going to be 3.35 to 3 significant figures. Looking at the critical value from the critical value table, our degrees of freedom is 21 because 10 plus 13 minus 2 gives us 21. And looking down, because this time it's a two-tailed test, we have to half our 5% significance level, which gives us 2.5%. So 100% take off 2.5% means that we're looking down from 0.975 down to 21, which gives us 2.080. So then, as the size of the test statistic is bigger than the critical value, we reject H naught. At a 5% significance level, there is sufficient evidence to suggest that the mean amount dispensed by A is not 3 millilitres more than B. And we could kind of tell that from the beginning. It's a bit of a silly question because we're saying that A gives off more than B when we can already see, well, the mean of A is smaller than the mean of B, and we're saying that A is 3 more than B. So also reading through that question, there's no stating that the amount of drink dispensed from A or B is normally distributed, so that has to be one of the assumptions that we are making. So I'd now like you to pause the video again if you haven't already and try the second Now You Try. Okay, so hopefully now you've tried the second Now You Try question. So now we've got a factory receives deliveries of an electrical component from two suppliers, A and B. The resistance of these components are critical. Inspectors are checking whether, on average, the resistance of components from supplier A are the same as from supplier B. The resistances are measured from the two random samples. The results in ohms are as follows. So then we've got our data and we're asked to carry out a 5% significance level. So we're seeing if they're the same. So that's a two-tailed test. So our H naught is that mu A equals mu B. Our H1 is that mu A is not equal to mu B. And you can see here again, I've got my definitions. Mu A is the population mean resistance from a component from supplier A. And population mu B is the population mean resistance from a component from supplier B. I then put this information into my calculator and got this information here. Then use that to find SP squared. As you can just about see in my screen still here, that gave me an answer that was in standard form. So I wrote it out as a normal number to show the examiner what I was using. Then when I was doing T, I ended up with a negative. If you put those numbers the other way around in the numerator, remember, you would just end up with a positive version of this. I ended up with the negative one, so then I had to use the size of the test statistic was 2.81. The degrees of freedom was 15. And again, when we're looking up our critical value, it's a 5% significance level, but this is a two-tailed test, so we have to half our 5%, which gives us 2.5%, which means we're looking down from 0.975 and across from 15, which gives us 2.131. So then the size of the test statistic, or like I said, if you did those the other way around, that'll just be a test statistic. It's bigger than the critical value, so we reject H0 at a 5% significance level. There is sufficient evidence to suggest that the mean resistance from a component supplied by A is not the same as from supplied by B. Remember, it's a two-tailed test, so it's always going to have not in the conclusion. And again, just checking back at the information that we were given here, this time we were told that they were two random samples, but nowhere here does it say that they were normally distributed. Because we are using the t-test, it's a small sample, we need those populations to be normally distributed. So right at the bottom, I've wrote that as an assumption. So make sure whenever you get one of these questions, always check, is it normal or is it T? Do I have the information for the sample or the population, and is my sample large or small? And you should always think about that very carefully. Always check that the language that you need is in the question. Remember, for the normal one, if it was a large sample, we didn't need for it to be normally distributed. But with all the time with T, it has to be normally distributed. It needs to state that somewhere. And for any of these, it always has to be a random sample. So next time, we're going to be moving on to having a look at the paired T test. Thank you very much for listening.